I guess I can start. Okay, so my name is Saniya. I am now a postdoc at EPFL at the Observatory of Geneva, but the work I'm actually going to talk about today has started when I was still doing my PhD at the University of Birmingham, and so that was supervised by Andrea Miglio. And so I will be talking about our investigation of the Gaia EDR3 parallax systematics using cool giant stars observed by Kepler, K2, and TESS. So as you all know already, Gaia EDR3 has provided amazing data that generate a huge interest in the astrophysical community, but there are still some known systematics involving position, color, and magnitude that can affect the reported Gaia parallaxes. And so the sky maps here, so they show the smooth median parallaxes for the quasars, on the left for DR2 and on the right for EDR3. And so the Gaia team reported a global offset of minus 17 micro arcseconds for the latest data release versus minus 29 for DR2. Also with EDR3, now there is a 0-point correction model that has been proposed by Lindegren et al. Depending on the ecliptic latitude, the G magnitude, and the effective wave number. And this is based on a sample of quasars, physical binaries, and the Large Magellan Clouds. So on the right, we see the effect of this correction on the quasars. So on the left, we have the results for the 5-parameter astrometric solutions, and then on the right, the same, but for the 6-parameter astrometric solutions. And each panel shows the weighted mean parallax of the quasars as a function of magnitude, effective wave number, and ecliptic latitude from the top to the bottom. So the parallaxes without any corrections are the black lines, and then once the correction is applied, all of these are shifted towards 0, which is expected since we are looking at quasars. And then in the literature, there have been several applications of this 0-point correction model. And a couple of these studies have also suggested that including this correction could sometimes lead to an overestimation of the parallax offset. So we will also see like what we find in our study. So this is a sky map showing the location of the different asteroseismic fields that we are looking at. So we have Kepler, 17 K2 campaigns, and then also the TESS 1000 continuous viewing zone. And I've also indicated the different observation lengths. So we can expect the K2 data to be of lesser quality. Then, so for the asteroseismic constraints, we consider two independent approaches. So one from Moser et al. And another one from Ellsworth et al. So in the remaining of the discussion, I will focus on the second pipeline. And then for K2, we also tested two different sets of spectroscopic data. So one from Apogee DR17 and another one from Gaia EDR3. So this allows us to have an idea of the systematics that are due to the spectroscopy. But then in order to keep a completely homogeneous sample in terms of spectroscopy, we are focusing on the Apogee constraints, as that's also what we are using for Kepler and TESS. So just a quick slide to understand how we can get parallaxes using Apogee. So we start with the seismic scaling relation for the radius, which combines nu max and delta nu, which are the frequency of maximum oscillation power, and the average large frequency spacing, which are illustrated on this power spectrum on the right. And then we also need an independent estimate of the effective temperature, which we get using spectroscopy in our case. And this is then combined with the Stefan Boltzmann law in order to compute the asteroseismic parallaxes. And for that, we also need information on the apparent magnitude, the barometric correction, and the extinctions. So this is the general idea on how one can get asteroseismic parallaxes. Now, in our study, all of these observational inputs go into a Bayesian code, which is called param. And so param does the comparison between these observations and a grid of stellar evolutionary tracks in order to compute the probability density functions for fundamental stellar parameters, which means that Param is a model-dependent method, but it has proven to give results in good agreement with independent studies, for example, for Gaia EDR3, which is why we decided to focus on this in this investigation. So here I'm showing a plot of the parallax difference of Gaia minus seismology as a function of the G magnitude. So the top panel shows all the samples combined together, and then the bottom panels, they show Kepler, K2, and TESS separately. First for Kepler, we find an offset that is slightly lower than the one we had found in Gaia EDR3, and we find that there is a non-linear trend as a function of the G magnitude. And so if we look at this figure from the catalytic validation paper, we see that this feature is expected already, and it is also removed if we do apply the Lindgren correction. So after correction of the parallaxes, then the relation with the G magnitude becomes flat. And so this trend here happens at specific G magnitudes, which could be thus related to the window calibration and gating mechanism in Gaia. So these are all the K2 campaigns combined together. So if we look at the individual campaigns, then these have a certain range of parallax offsets, which is indicated here. And then if we apply the Lindgren corrections before calculating the offsets, then we find that a lot of these become positive, which is another sign that the Lindgren correction could not be exactly appropriate for the asteroseismic samples that we are looking at. And so we also see again this nonlinear trend, even though it's not as clear as in Kepler. And what we notice as well is the larger scatter in the K2 sample, which we already expect because of the quality of the asteroseismic data, which is not as good as Kepler's. But then if we look at this plot here, it shows the parallax uncertainties in EDR3 on the sky. And so we see that the uncertainties are larger all along the ecliptic, which is where all of these K2 fields are located. So these larger scatter could be a combination of both the quality of the asteroseismic data, but also of the Gaia data as well. And finally, so this is what we have for TESS, for which the sample is restricted to bright giants with G lower than 11. So these are some summary plots. So now we are mainly looking at the median offset. So we have, again, the parallax difference between Gaia and seismology as a function of the ecliptic latitude, the G magnitude, and the effective wave number. So the first thing is that the asteroseismic offsets that we measure are mostly negative. So we have TESS here, Kepler here, and then here we have all the individual K2 campaigns. And because they are all along the ecliptic, we expect them to occupy the same locus in this plot. And then in terms of magnitude and color, so with respect to quasars or red giants, they are going to be brighter, and they also have a redder color. So in that sense, they are complementary with the analysis that had been done with by the Gaia team. And so these two plots here, they show the median offset being by magnitude and μf, so that we can also see the trend with magnitude and color. So again, here we see that we have this nonlinear trend as a function of G, which is shifted depending on the median offset corresponding to each of these fields. And then as a function of the effective wave number, we may see a trend whereby we have more negative offsets as we go towards lower effective wave numbers. And finally, we also did an independent check of our analysis using the magnitude of the red clump. So this plot here shows the magnitude of the clump in the K-band as a function of the galactic latitude. And so we have different samples here. So the first one are these colored symbols here. They correspond to our asteroseismic samples. So these are the 2 mass K-band absolute magnitudes that have been computed by Param. And then we also select Gaia EDR3 sources, which are selected in each of these fields. And we compute absolute magnitudes using the parallaxes, either correcting them with the Lindgren correction or not correcting them at all. And so the resulting magnitudes that have not been corrected are the ones with filled triangles, and then the open triangles are the one after applying the Lindgren correction. And last thing I'm showing on this plot as well are the colored lines. So these are predictions from models which come from the review by Leo Girardi. And so these 2 dashed lines here, so these correspond to young models, so like 5 gigayear. Then the dotted lines are for old models, 12 gigayear, and orange and purple correspond to metal rich and metal poor stars, respectively. So these values I've chosen here are so that they are representative of the asteroseismic fields that we are looking at. So these would be the lower and upper ends of the age and metallicity distributions. And so what we can get from here is that the asteroseismic samples, they fall well within the predictions, and they also show a trend with the galactic latitude. And this trend, we also see it for the Gaia EDR3 samples without including the Lindgren correction. But when we do include the correction, then this trend becomes like more flat. And so this could be another sign that the Lindgren correction is not exactly appropriate for our cool giant stars. So this leads us to the conclusion. So with all of that, we've been able to show that there is a clear spatial dependence of the offset, thanks to the various asteroseismic fields that we have been looking at. And we also found, like previous independent studies, that including the Lindgren correction could lead to positive offsets, for example. So these shows us that we need to consistently determine the parallax systematics that are applicable to the sample of interest. And finally, we also demonstrate that asteroseismology is a powerful test of the Gaia systematics. Red giant stars are single stars. They have measurable parallaxes. They do not show large amplitude photometric variations, and they also do not rely on assumptions like the Hubble constant, for example. And on the other hand, Gaia can also help testing the accuracy of the seismic parallaxes, especially for nearby stars where the parallax offset is not as important. So I think there is a lot of synergy that is quite interesting between Gaia and asteroseismology, and so that will continue with the future Gaia data releases. So thank you.
Thank you very much for a really interesting talk about the synergy of different surveys and studies. It's really great. Do we have any questions? Of course, we have some questions, please.
Can you show again the trend of parallaxes of color?
Yes.
Which is the right?
Yeah, this one.
Which is the range of variation of that trend? It's the same. The values in the y-axis are the same that in the left plot?
Yes, they are the same. The axes are the same, yes.
This could be also tested with stars belonging to clusters, but they have to have the same parallax, all of them.
Mm-hmm.
So
yeah.
In the difference between parallaxes, individual parallaxes and the median parallax of the cluster,
yeah.
would give also a trend if there is a I think we tested that in the validation group in Gaia, and we didn't found that, but I don't remember exactly. That was a time ago.
Mm-hmm.
I don't remember, but I think we already tested that, and we found the dependence with the proper motions, but I don't remember that dependence on huge dependence on.
Yes.
On clusters, but you are on the range of the giants only. Is that correct?
Yeah.
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 Thank you for the question and thank you for the answer. I see no more questions and no more questions online. So thank you for the presentation.
Thank you.
Our